we present a software tool called fastForce. fastForce takes laser cut structures that would normally break and reinforces them in real time. The lower plate of this handle now extends all the way through the sides of the wheelbarrow, making it very robust. The handles are now 45 times stronger, easily carrying this additional load. We set ourselves two objectives in designing fastForce. First, reinforcement should happen automatically. Participants of our study often were unaware of structural flaws in their design. To illustrate this point, consider this model. Can you locate the points of failure? The head of this model will break in a very similar way to the wheelbarrow handles. However, other parts of the model break in other ways. fastForce identifies them automatically for the user. Second, reinforcement should happen in real time. This is crucial whenever users need to make a design decision. In this example, the user designed the left guitar stand to be more aesthetically pleasing, but designed the right one to be more sturdy. fastForce ensures structural stability in real time. This allows the designer to focus and elaborate on their preferred model. Finite element analysis and the resulting deformation model excel at finding structural flaws. However, it took 8 hours, which is 6 orders of magnitude more than the 30 frames per second we require. When we classified the issues identified by finite element analysis, we realized that they fall into two categories. First, beams breaking due to high force, and second, failures due to finger joints being pulled out. The second class of failures can break the model with very little force. We call them critical failures. Critical failures are the result of structural flaws in the model. That is, cases where a beam had degenerated due to finger joints being subjected to tension. A small bending moment can easily pull out the joints. Essentially, the beam is reduced to a single plate, which breaks orders of magnitude more easily. The great news is that if we limit our views to these critical failures, then the problem becomes tractable in real time. We classified the points of failure into 6 different primitives. This primitive is a simplification of the wheelbarrow's handle, which, as we described, breaks easily under tension. fastForce reinforces the point of failure by extending a plate parallel to the existing one. In our technical evaluation, we found that the structure can now resist bending moments 39 times stronger. This creates a reliable connection between the two substructures. Since all reinforcements are placed on the inside, the outer shape remains the same, preserving the user's design. The remaining points of failure are reinforced in a similar way. We analyzed 400 models downloaded from the Cube model repository and found that 71% of them were subjected to at least one of the 6 points of failure. Here we see the walkthrough of a user modeling the wheelbarrow. We integrated fastForce as a plugin into Cube, a 3D editor for laser cutting. In case of the wheelbarrow, fastForce takes on average 14 milliseconds to perform its structural analysis, allowing it to run automatically and in real time. This fully automatic interaction eliminates the need for any user interface, allowing us to also address non-engineering audiences. The fastForce algorithm is divided into 2 parts. In the first step, fastForce identifies all the points of failure in the model. To speed up its analysis, fastForce represents the object as a simplified graph. The plates are represented as nodes, while the joints between the plates are represented as edges. Since finger joints are weak against tension, fastForce identifies joints that can be subjected to tension load and removes them from the graph. In case of the wheelbarrow, this splits the graph into disconnected components, which means that some points of failure will also be completely disconnected under load. Similarly, some parts of the graph are only connected by a single node, which means that some points of failure in the object are only connected by a single plate. This means that they are weakly connected components and will break apart under very little load. We repeat that process one more time to identify the last remaining issue. Using this approach, fastForce identifies all points of failure in an object. In the second step, fastForce reinforces the points of failure. fastForce starts by reinforcing the weakest points of failure. To stop the tray from falling in, the bottom plate is extended and anchored into the sides of the wheelbarrow. To stop the legs from being pulled out, fastForce chooses two parallel plates and extends them into the body. The handles and back legs are reinforced in a similar way.